Okay, so let's do a quick recap of what we saw in the last class. In the last class, we discussed this notion of the VC dimension and saw a bunch of examples for a few toy hypothesis classes. We computed the VC dimension, right? And towards the end, we showed that if a hypothesis class has infinite VC dimension, then it is not pack learnable. And in fact, the minimum number of samples required for you to be able to achieve some epsilon delta error is it's kind of it's lower bounded by half the size of the largest set that is shattered by the hypothesis class, right? So if the hypothesis class shatters a set of size 2n plus 1, then you need at least n plus 1 samples in order to be able to learn well. You can't do with any less than n samples, right? So this leads us to this notion of the fundamental theorem of pack learning, which says that if we are looking at binary classification with the 0-1 loss, then the following statements are equivalent, which is that H has to satisfy uniform convergence property, ERM is an agnostic pack learner, H is agnostic pack learnable, H is pack learnable, and ERM is a pack learner for H, and H has finite VC dimension. So effectively, in the binary setting, all of these notions are equivalent. If you are able to learn a particular hypothesis class well, then it must satisfy the uniform convergence property, and you can use ERM to learn this hypothesis class. You don't need to look beyond ERM to devise a good learner. All right, and one way of determining whether a particular hypothesis class is pack learnable or not is to find the VC dimension. If it is finite, then it is pack learnable and therefore agnostic pack learnable. And if the VC dimension is infinite, then there's no hope. No matter what you do, there's no point in looking for a learner that achieves arbitrarily small epsilon and delta error, right? And we've seen the equivalence almost in one side completely. The only thing that was left to prove was that if H has finite VC dimension, then the following properties hold. And for that, it's enough to show that if H has finite VC dimension, then either ERM is an agnostic pack learner for H, or H has the uniform convergence property. All right. In fact, we'll show that H has the uniform convergence property, and by way of that, ERM is also an agnostic pack learner for H. Okay. And in fact, we'll see an upper bound on the sample complexity that is required to achieve an epsilon delta error, and therefore for uniform convergence in terms of the VC dimension. But when deriving this, we'll also see a number of other measures of complexity. In fact, we'll see two different measures of complexity. One is the Rademacher complexity. We'll see what that is. And the other is the so-called growth function. So we'll first derive an upper bound on the sample complexity in terms of the Rademacher complexity. Then we'll upper bound the Rademacher complexity in terms of the growth function, and then we'll upper bound the growth function in terms of the VC dimension. All right. So all of these three measures are good enough measures of complexity. And again, it's tight in this particular order. So if you have a tight bound on the Rademacher complexity, then you don't need to go to the VC dimension at all. Because the bound that you get using the VC dimension will be more loose than the bound you get using the Rademacher complexity, which will be more loose than the bound that you get using the growth function. Okay. It's for classification only. So that's a good point you raise. So the VC dimension, so all of these bounds that involve the VC dimension hold true only for binary classification and specifically the 0-1 loss. It does not extend to other classification or regression problems. But the Rademacher complexity, as we'll see, it's a valid measure of complexity in a much more general setting, much more general supervised learning framework. Okay. So we'll start, that's why we will begin with very general assumptions, and then we'll restrict our class of problems as we go along. All right. So first, let me define this, what I mean by the Rademacher complexity. So in fact, we'll define two Rademacher complexities. The first is what I call the empirical Rademacher complexity, which, as the name suggests, is an empirical measure, and in particular, it depends on the data set that you see. It's a random variable that depends on the data set. So the empirical Rademacher complexity, which I'll denote RC subscript S, and I'll have a hat to denote that it's something empirical. The subscript S denotes that it depends on the data set S. And of course, this depends on the hypothesis class H. Implicitly, this also depends on the loss function, but I'm not indicating that explicitly. So this is equal to, for this I'll define a sequence of IID random variables called Rademacher random variables. So Rademacher random variables are those which are like Bernoulli random variables, except they take values +1 and -1 instead of 0 and 1. All right, so it's an expectation over these Rademacher random variables, which I denote sigma. So sigma underline, that's a vector of Rademacher random variables. So each sigma I takes +1 with probability half and -1 with probability half. So it's basically uniform on 1, -1. So it's expectation over all possible sigma of the following quantity, the supremum over all H in the hypothesis class of 1 over n summation I equal to 1 to n, the loss of achieved by H on the ith sample. Okay, so this is the definition of the empirical Rademacher complexity. This is a random variable which depends on xi by I, but it's a complicated looking function, and there is also a new set of random variables. So this is missing. This is missing. Yeah. Less. There should be a sigma I L of H of xi yi. Right. So what's the intuition behind this Rademacher complexity? This quantity over here, the quantity inside, let's say for a given H, this quantity, you can interpret this as an inner product between the vector sigma and the vector of losses. Correct? So sigma can be interpreted as pure random noise. It has mean 0. Right, the entries are mean 0, and whatever, it's uniform +1 -1. So the supremum over all possible H of this asks for what is the maximum possible correlation that you can have between pure random noise and this loss vector. Okay, that's sort of a one way of interpreting this particular quantity, and this is of course averaged over sigma. Okay, so this is if this quantity, if the Rademacher complexity is large, then it means that the worst case correlation between the loss vector and pure random noise is high. That's sort of a very high level interpretation of this quantity. All right. The Rademacher complexity is just the expectation of this with respect to the data set, nothing more. I'll denote this RC of H, and I'll have an N subscript N to denote that this is a parameter. This is parameterized by the number of samples that you have. This is nothing but expectation over S of RC hat S of H. So, before we continue, let's try to think about why this Rademacher complexity should be a measure of complexity of your given function class. Okay, so let's, of course, there is this L of H of xi yi appearing, which is a little bit mysterious, but let's assume that let's not think too much about L for now for a given loss function. Let's try to think about what would happen if H were if the hypothesis class were very rich. Okay, so if you have a huge number of functions, let's assume that the hypothesis class is the set of all possible functions, right? Then for a given configuration sigma I, right, there would be one choice of H which would be fully correlated with this any configuration sigma 1 through sigma n. Right? Because the function class is rich enough, you should be able to find at least one such H, which would mean that this quantity would be high because I'm taking the supremum over all possible H. There is one H for which this correlation is the maximum, and therefore this quantity supremum would be high. And since this holds true for every single configuration of sigma i's, it also holds true in expectation. Right. Now, on the other hand, if you could not generate too many functions, suppose that there is only one function in your function class. It's a trivial and useless example, but still it gives some intuition. Let's suppose that L of H of xi comma yi is the same. It's almost the same for all the xi's and yi's. Then the supremum would essentially be more or less a constant. Right? There's not too much variation in L of H of xi comma yi, which would mean that when you take the expectation over sigma, this would be very small, right? Because if H is not rich enough, then this would be more or less like a zero mean random variable. The correlation would be small because you're taking the expectation over sigma. Okay, so it's not possible to always find a H such that you have full correlation with all possible configurations of sigma. Okay, that's sort of a high level intuition for the Rademacher complexity, or why it should represent complexity of a hypothesis class. It's still not clear why this is the right measure of complexity, but still intuitively it is some measure of complexity of the hypothesis class. Which one? Okay, so the loss function could be anything. Okay, this definition makes sense irrespective of what the loss function is.
Does it depend on n?
Which one?
The Rademacher complexity.
The Rademacher complexity does depend on n, right?
The actual to the
It does, because you're only taking expectation over xi, yi. Now, if you did not have this particular supremum over here, then I agree this does not depend on n. But because of the supremum, it can potentially depend on n. It's not straightforward. You can't just exchange the supremum and the expectation. If you exchange the supremum and expectation, surely the right-hand side would not depend on n. But this can subtly depend on n. Okay.
On head star it will become 0.
Which one?
On head star.
Not necessarily, right?
Why? Because it's able to exactly have a exactly h equal to y. Like it becomes
So-
becomes
So if there exists a H star that achieves zero loss, then what you say is true. No, even then this Rademacher it does not hold true, because the Rademacher complexity is the supremum over all possible H, right? It's not the minimum over all possible H. So this kind of takes into account the worst case function in your hypothesis class, very loosely speaking. I don't say that it is actually the worst case, because in the end you're trying to find out, because this depends also on the particular configuration sigma 1 through sigma n. For a given configuration, there are 2 to the n possible configurations of sigma, and for each configuration of sigma, the supremum could be achieved by a different function h. And it has nothing to do with the h that minimizes or maximizes the empirical risk. Right? If the sigma I were all ones, then basically this would correspond to the one which achieved the maximum empirical risk. If sigma I were all minus 1, then it would be the one that achieves the minimum empirical risk. But for any other configuration, it could be something totally different. Okay, so you can't, the one that achieves this maximum, it does not give you any information about how good or bad it is, the class is. Okay. But if the hypothesis class is rich enough, then you will always be able to find some h that correlates strongly with this given configuration. Okay. Great. So we want to prove the following fairly general result, which says the following. So right now we'll not focus on classification or regression. It could be any general supervised learning problem. So consider any supervised learning problem with the loss function bounded between 0 and 1. If it's not bounded between 0 and 1, you can always sort of renormalize things. There's no loss of generality in this particular assumption. But certainly I want the loss function to be bounded. That's the only requirement that I'm going to make. Okay. Then with let me state it the following way. For any delta greater than 0, with very high probability, with probability at least 1 minus delta, I have R of h to be less than or equal to Rs of h plus 2 times the Rademacher complexity of the hypothesis class h plus square root of log 1 over delta by 2n. This is at least 1 minus delta. Right? So basically this whole quantity is the amount epsilon. This whole thing is your epsilon. I could write this in terms of epsilon and say that for all n greater than something else. Correct. That's a good point. And this holds true. Things here. This holds true for all h in my hypothesis class, right? So this is in fact the very statement of uniform convergence, right? For every h in my hypothesis class, the generalization error is epsilon close to the corresponding empirical risk, and the epsilon is precisely given by this quantity, 2 times the Rademacher complexity plus square root of plus something that decays as 1 over n. So as 1 over square root of n. So as n becomes large, at least this second term goes down to 0, and hopefully the Rademacher complexity, we don't know yet how the Rademacher complexity depends as a function of n.
Is there a difference if you put the for all h belongs to h inside the bracket and outside?
Yeah, it does. What do you? Yes, it does, right? So if it's outside, for every h, if probability is greater than or equal to 1 minus delta, that is automatically just guaranteed by for any hypothesis class. Right? It's just for any specific h, it concentrates. Right? You are guaranteed as long as L is sub-Gaussian and h is any hypothesis class, any arbitrary hypothesis class, you have that for every h in h, the probability that R of h is blah 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 is greater than or equal to 1 minus delta. But here you are saying something more. You are saying that you are trying to find the probability that for all h, this holds. Right? Which is in the previous case, you have a bunch of events, one event, each event depending on h, and here it's an intersection of events.
So here I can write in the RHS supremum over all h when h belongs to that thing. It is equivalent, right? If I write for all
Be
RHS,
careful because the right hand side of the inequality also depends on h.
means inside the probability R of h is
You're right, we'll do that effectively, but you'll have to bring the Rs of h to the left hand side and then take the supremum. Otherwise, it doesn't hold. Okay. So this is one bound that depends on the Rademacher complexity. We'll give another bound that depends on the empirical Rademacher complexity. Right. So the probability, it's very similar. R of h less than or equal to Rs of h plus 2 times the empirical Rademacher complexity of h plus, now there's an additional penalty term, it is 3 times square root of log 1 over delta by 2n. for all h in the hypothesis class, this probability is at least 1 minus delta. Okay, small change. There should be a 2 in here. Yeah.
What does the Rademacher complexity tell us about the hypothesis class? Let's say if it is very open, what inference can we take out?
So as I said, like very loosely speaking, the Rademacher complexity measures the correlation you can have with pure random noise. So if there is high correlation with pure random noise, it means that the function class is very rich. Okay, this is again very high level intuition.
Sir, can I interpret it this way? Like supremum H belongs to capital H. We are on purpose picking the bad class out of all H. We are on purpose picking up the bad class so that we will maximize the class. Whatever.
So again, that's why I said you have to be careful in that sort of an interpretation, because the one that maximizes this, you're not really over here. You're not actually maximizing the loss, right? You're taking the supremum of not the empirical risk, because you're weighting by these sigma i's, and sigma i's are positive and negative, right? So the ones that are weighted negative means that if L is large, then it becomes more negative.
So can I say that it is the complexity is just a measure of quantity of bad classes in capital H?
Not really. So I would not interpret too deeply into this particular quantity. Okay, but we'll see where this appears from. Okay, so this was an intuitive interpretation, but there's something more specific what this quantity represents. Okay, not exactly represent, but strongly bounds. All right. So, okay, let's leave Rademacher complexity out of the picture just for a moment. Our goal is to somehow prove some sort of uniform convergence, right? Uniform convergence, or that ERM performs well, correct? So since ERM performs well, let's try to go back to what we did for finite hypothesis classes. Right? In the case of finite hypothesis classes, I was able to find this particular probability, that is without that for all h in h. For every single h, this probability was small. Forget about, let's try intuition or approach. Right, so for any h, just through an application of Hoeffding's inequality, I know that the probability that R of h is whatever greater than or equal to Rs of h plus epsilon is upper bounded by some 2 times e to the power minus some constant times n epsilon square. Right, just through an application of Hoeffding's inequality. Now for finite hypothesis classes, I can take a union bound on all possible h. So the probability that R of h, so this is the bad event, that R of h is greater than or equal to Rs of h plus epsilon for some h. Remember that the complement of this event is that R of h is less than or equal to Rs of h plus epsilon for every h. The complement is R of h is greater than Rs of h plus epsilon for at least one h. That's the good event, this is the bad event. So this is basically a union over all h of R of h greater than or equal to Rs of h plus epsilon And if the number of classes or the number of predictors were finite, then I could just go ahead and use a union bound. I would be done. Right? And I could get some bound on the sample complexity. But I can't do that anymore because I made no such assumptions on H. I want to do this for infinite hypothesis classes. So clearly this approach is not going to work. So what more can we do? Well, what I can do is I can do precisely what you suggested. We look at the quantity supremum overall H of R of H minus Rs of H. Right? So if this quantity is less than or equal to epsilon, it means that for every H, R of H minus Rs of H is less than or equal to epsilon, which is exactly what I wanted here. Right? This is exactly the event that I'm interested in. The challenge with looking at this random variable is it's no longer something that's simple. I can't write it as a simple average of IID random variables. It's a function of IID random variables, but it's no longer a simple function of IID random variables. Okay, so this is the quantity that I'm interested in. Basically, I want to know what is the probability that this quantity is, let's say, greater than or equal to epsilon. Okay. Now, again, we have all the tools that we need to look at this random variable. We'll see that this is a function that satisfies the bounded differences property. The function supremum over H, R of H minus Rs of H. Now, since it satisfies the bounded differences property, we know that we can just go ahead and use McDermott's inequality. This concentrates slightly around the mean. So that's already given to us. That's not very difficult. At least conceptually, it is not very difficult. Proving that this is a function with the bounded differences property may take a little bit of effort, but after that point, we are done. We know what to do. So that's one thing, concentration is taken care of. Okay, so first, we'll show that this quantity, this function over here, satisfies the bounded differences property. And then we can use, and hence concentrates. So we can prove a concentration bound. But as we've seen when we were dealing with concentration inequalities, proving concentration in many such applications when the function is complicated is not too hard, because you can use one of these, either the Efronstein or the bounded, McDermott's inequality or something else to prove concentration. The more difficult part is to find out what it concentrates to, because you need to be able to compute the expectation. It concentrates to the expectation. So then we will bound the expected value of this particular quantity. And we'll see that we can upper bound the expectation as in terms of the Rademacher complexity. In fact, we'll show that this is less than or equal to 2 times the Rademacher complexity of H. So that's another operational interpretation of the Rademacher complexity. It's basically the largest, or although it's not exactly the same, it bounds the maximum deviation possible between the empirical risk and the average risk. All right, it's not exactly equal to, it's an upper bound, but it's a decent enough upper bound, as we'll see. Okay, so let's go through each of these steps. So step 1 is to show that this quantity satisfies the boundary differences property. So let me define phi of S to be the supremum over all H in the hypothesis class of R of H minus Rs of H. This depends on the hypothesis class as well, but I'm not indicating that in phi of S. So how do we prove the boundary differences property? What should we do?
You need to replace one of the sample with identical.
Correct. So basically you take two configurations S and S prime, two data sets S and S prime, which differ only in one sample. All right. So assume that S and S prime are two arbitrary data sets. That differ only in the ith sample. Okay, so we want to know what is phi of S minus phi of S prime. Right? We want both a lower bound and an upper bound, but again this is kind of symmetric, so therefore if you get an upper bound, then you also naturally get the lower bound is just the negative of that particular quantity. Right? So phi of S minus phi of S prime is it's what? So it's basically the supremum of R of H minus Rs of H minus the supremum of R of H minus Rs prime of H. All right. Now an upper bound is enough. So this is less than or equal to, so supremum of A, maximum of A minus maximum of B is less than or equal to the maximum of A minus B. So this is less than or equal to the supremum of the difference. So supremum of R of H minus Rs of H minus of R of H minus Rs prime of H. This R of H and R of H get cancelled, and I end up with just Rs prime of H Rs prime of H minus Rs of H, which is nothing but 1 over n times L of H of xi yi minus L of H of xi prime yi prime. Right? How large can this quantity be? 1, right? So it's 1 by n. So phi of S minus phi of S prime is at most 1 over n. So phi of S prime minus phi of S is also at most
Is it
1.
because it is a zero one loss?
Which one? Not because it's because you're assuming that the loss is bounded between 0 and 1. Right? It does not necessarily have to be 0 or 1. Could take any value in the range from 0 to 1. If there is some other bound, if it's bounded between 0 and something else, some alpha, then this would just be alpha over n. All right. Great. So phi of s minus phi of s prime is at most 1 over n. It's at least minus 1 over n. Great. So now I can use the bounded differences condition. I can use McDermott's inequality and basically show that I have convergence. Right? But I'll sort of use a one-sided McDermott's inequality in this case. I can in fact prove that mod phi of s minus expectation phi of s is upper bounded by so basically I can bound the following quantity phi of s minus phi prime of s greater than or equal to epsilon. But for me, it's enough to bound phi of s minus phi prime of s greater than or equal to epsilon. Because I just want to show that r of h is less than or equal to rs of h and so on. But using this, I could potentially also bound the maximum deviation. Okay. So this quantity is upper bounded by, just by using McDermott's inequality, this is upper bounded by e to the power minus 2 epsilon square divided by summation ci square. Now, because I'm using a one-sided tail bound, on the right hand side I just have e to the power of minus this quantity. If I wanted a bound on this entire quantity, then there would be another 2 sitting over here. Not a major difference, it's just because I want to get rid of that 2. Okay, and ci in this case is 1 over n. So therefore, in the denominator I have a summation over I of 1 over n square, which will amount to just 1 over n. So this is e to the power minus 2n epsilon square. All right. So if I want this entire quantity to be less than or equal to delta, then that amounts to just choosing epsilon square to be equal to log 1 over delta divided by 2n. So the probability that phi of s minus, I'm sorry, I messed this up a little bit. This should be expectation over s phi of s is greater than or equal to epsilon, which is log square root log 1 over delta by 2n is less than or equal to delta. So if you go back to what we were trying to do over here. So this is the result that I ultimately want to show. This second term basically comes from the concentration. So this remaining term therefore should be the expectation of, or it should be some bound on the expectation of supremum over h, r of h minus rs of h. So this quantity is an upper bound for expectation phi of s, and in fact this quantity is your epsilon. Okay, so the next step is to find expectation of phi of s. So let's look at expectation over s of phi of s. Let's expand this out. This is expectation over s of supremum over all h of r of h minus rs of h, right, by definition. But r of h is expectation of rs of h, right, by definition. So just to indicate, because I have s over here, I'll write this as supremum over all h of expectation with respect to s prime, where s prime is an independent and identically distributed copy of s. Rs prime of h minus rs of h. Okay.
Even if we replace S dash with S, the second line will be equal to, even if we replace S dash with S.
It is, but then the notation becomes messy, and in particular I'm separating out the s prime with respect to s because next I'm going to take the s prime outside the supremum. So this is less than or equal to expectation over s of expectation with respect to s prime supremum rs prime of h minus rs of h. Just because the supremum of a sum is always lower bounded by the sum of the supremums. Right? Because expectation is nothing but a sum, it's just an average, right? So an average of supremums is always an average of supremums is always an upper bound for the supremum of an average. Yeah, Jensen's inequality, if you want to take that. Okay. Any questions so far? Fine. Okay, so now I'm going to play around with the quantity inside the expectation. Then the next, let me expand out rs of h and rs prime of h. This is equal to expectation with respect to s, expectation with respect to s prime of supremum over all predictors h 1 over n times summation I equal to 1 to n of L of h of xi yi, or let me call this xi prime yi prime, minus L of h of xi yi. Now, now at this point, I'm going to make a jump. I claim that this is equal to expectation with respect to S, expectation with respect to S prime, expectation with respect to sigma. Sigma is IID plus 1 minus 1 uniform of supremum H in the hypothesis class of 1 over n summation I equal to 1 to n sigma I times the quantity that I have over there, L of H of xi prime yi prime minus L of H of xi yi. So why is this particular statement true? This is true because this quantity, in fact, it's more helpful to take this to think about it with the expectation order of expectations reversed. All right, this is equal to expectation with respect to sigma, expectation with respect to S and S prime of this particular quantity. Now the quantity inside is essentially symmetric in X and X prime, in S and S prime, right? So for a particular sigma I, right, if sigma I is positive, then it's exactly what you had previously. If sigma I is negative, it's basically the two flipped. xi yi flipped with xi prime yi prime. But since this is symmetric in S and S prime, I can just flip the two. It doesn't change the quantity. Right? So in particular, if you want to just sort of, I would encourage you to prove this more formally, but just so that you get some intuition, you can look at maybe a much simpler case when maybe n is equal to 1. Okay, this L, all of that business is not particularly important, right? Some function. So this is effectively of the form expectation over sigma, expectation over S, expectation over S prime of, assume that n is equal to 1, just for the sake of intuition, supremum over H of let's say L of let's say S minus L of S prime. Let me index this by H. Okay, just some notation that I've introduced over here so that it looks cleaner. Okay. Now this is the same. If I sort of write it down, this is equal to expectation over S prime of, let's say, half supremum over H LH of S minus
Shouldn't there be a sigma?
sorry, sigma?
Shouldn't there be a sigma?
Which sigma?
Sigma I we are taking as 1.
I'm taking just sigma as 1, right? I'm just taking n equal to 1 for convenience.
Then sigma 1 would be
Sigma times LH.
Correct. Okay, let's not worry about sigma at all at the moment. Okay, I'll bring in the sigma later. This is equal to, my claim is this is equal to supremum over H of L of H, LH of S minus LH of S prime plus half expectation S prime of supremum over all H LH of S prime minus LH of S. Because it's completely symmetric in S and S prime. Because S and S prime are independent and identically distributed. So S and S prime are just sort of variables, nothing else. Right? They're just placeholders. And you can swap between the two. Is this step okay? Okay. But then what is this equal to? It's exactly equal to expectation over sigma, expectation over where sigma is a Rademacher random variable, expectation over S and S prime of supremum over all H sigma times LH of S minus LH of S prime. Because the quantity over here is just minus LS of H minus LH of S prime. In getting the second term, I've just made a change of variable, nothing more. Right? I mean, I agree, this is just for n equal to 1, but exactly the same way you can also prove for a general n. Basically, for all those samples where sigma I is negative, we just swap. That's it. And because S and S prime are identically distributed, it remains the same. Okay, so well, we almost have exactly what we need, because what is this quantity? Let's go back to expectation of phi of S. This is less than or equal to expectation over sigma expectation over S and S prime of supremum over H of 1 over n summation sum over I L of H of xi yi minus L of y prime H of xi yi. Right. Now again, I'm going to make use of the fact that the supremum of a sum, I'm going to bound by the sum of the supremums. So in particular, because sigma I can take values plus 1 and minus 1, this is less than or equal to expectation over sigma expectation over S prime supremum over H 1 over n summation I sigma I L of H of xi prime yi prime plus expectation over sigma expectation over S prime supremum over h 1 by n sum over I sigma I L of h of xi yi. The sign doesn't really matter because sigma I is +1 -1 with probability half. But both of these quantities are exactly the same and they're equal to the Rademacher complexity. Okay, so this is equal to 2 times expectation over sigma, expectation over s, supremum over h 1 by n sum over I sigma I L of h of xi yi. Question?
We drop the S prime.
We dropped s prime because you see that each of the terms depends either on s or on s prime. So expectation phi of s is upper bounded by 2 times the Rademacher complexity of h. Here is an exercise using a similar approach, basically by showing that the Rademacher complexity also satisfies the bounded differences property. Satisfies a bounded differences property and prove that the probability that the Rademacher complexity RCN of h is greater than or equal to RC S hat of h plus square root log 2 over delta by 2n is less than or equal to delta over 2. Yeah. Okay. Now we've already shown, so this is an exercise. We've already shown that the probability that phi of s is greater than or equal to expectation phi of s plus square root log 1 over delta by 2n is less than or equal to delta, right? Or also probability that phi of s greater than or equal to expectation phi of s plus square root log 2 over delta by 2n is less than or equal to delta by 2, right? And expectation phi of s is basically upper bounded by 2 times the Rademacher complexity. Right? So the probability that phi of s is greater than or equal to the Rademacher complexity plus square root log 1 over delta by 2n is less than or equal to delta. All right, I'm just making use of this over here. Okay, and therefore if I have, let's say, 2 over here, then I have a delta over 2 here. And using this and the fact that the Rademacher complexity is close to, sorry, this should be 2 times the Rademacher complexity here. So combining this along with this here gives me the fact that, and using the union bound, this is just phi of s greater than or equal to 2 times the empirical Rademacher complexity of h plus 3 times square root log 2 over delta by 2n is less than or equal to delta. But this is exactly what we need, right? So for all, so probability that for all h in h, r of h is less than or equal to rs of h plus 2 times the Rademacher complexity of h plus square root log 1 over delta by 2n. This quantity is at least 1 minus delta. Questions? So effectively we just used 2 steps. One, we showed that this phi of s, which was supremum over all h of RH minus RS of h, this quantity is so we first showed that phi of s satisfies the bounded differences property, and then use MacDermid's inequality to show that phi of s concentrates tightly around its mean. All right, so this was step 1, and step 2 was actually finding expectation phi of s. That was not terribly straightforward, but we upper bounded that in terms of the Rademacher complexity, or to be more precise, 2 times the Rademacher complexity. And using a very similar approach, you can also upper bound using the empirical Rademacher complexity, although you can't upper bound it directly by the empirical Rademacher complexity because this depends on the data set itself. It's a random variable. But nevertheless, you still have a nice upper bound for this probability. Right? So it was just a combination of those two steps. Now at this point, in principle, we could just stop. We already have a measure of complexity, and we've shown that as long as the Rademacher complexity is, so this implies that if the Rademacher complexity is something that goes to 0 as n tends to infinity, then we are done. Right? Because it means that this epsilon can be made arbitrarily small, and that's all that we require. Right? That would imply pack learnability. But the problem with this approach is that in general, the Rademacher complexity is very hard to compute. In fact, there are results which show NP hardness of computing the Rademacher complexity. So that's why we have to resort to something much simpler. Because as you can see, the Rademacher complexity depends on n also. Right? It's not something that's easy to compute. In principle, you could try to compute it for a given, but this, if you go back to the definition of the Rademacher complexity, right? This Rademacher complexity depends on expectation with respect to S, which means expectation with respect to the distribution Pxy, and you don't know that. Right? So this potentially for a given distribution you could try to compute this quantity, but then we want this to be bounded by something for all possible distributions. So we want a distribution independent bound that tells us whether it's possible to do pack learning or not. Right? And that is precisely the advantage that the VC dimension gives us. Okay. But before we proceed to that, we look at sort of a simplification of the Rademacher complexity, a minor simplification of the Rademacher complexity for binary classification. So henceforth, we'll only be focusing on binary classification and nothing else. All right, because the VC dimension and so on is only true for binary classification with 0-1 loss. So let's consider binary classification. With 0-1 loss. In fact, we'll assume, since the label set is something that is arbitrary, right? It just has to be binary. 0 and 1 is something that we chose, but in principle I could also choose it to be +1, -1, or a comma b, or anything else. It ultimately boils down to the loss function. The loss function is 0 if yi is equal to yi hat, it's equal to 1 if yi is not equal to yi hat. So just for convenience, I'll use a slightly different representation. So I'll assume that each function h is a map from x to 0, 1 to +1, -1. So in other words, the label set is 1, -1. Right? The reason why I want to do this is then, if you look at L of h of xi yi, I can write this for the 0-1 loss. This is equal to 1 minus yi times h of xi divided by 2. Right? Because if yi, so h of xi is either +1 or -1, right? And yi is either +1 or -1. If both of them match, then this quantity is 1. The numerator becomes 0, and therefore the loss is 0 as we want. If yi does not match with h of xi, then this quantity is -1. So therefore the numerator becomes 2, and therefore 2 by 2 gives you 1. So this is exactly equal to the 0-1 loss. So for this binary classification, using this particular representation, I can simplify, get a slightly neater representation for the, let's start with the empirical Rademacher complexity. This is equal to expectation over sigma of supremum over h 1 by n sum over I sigma I L of h of xi yi, which is nothing but 1 minus yi times h of xi divided by 2. All right. Now I can split the two terms. This half minus yi h of xi by 2. This is equal to expectation over sigma. This is since the first term doesn't really depend on h, this is nothing but expectation over sigma of 1 over n sum over I sigma I by 2 minus, or let's take plus, expectation over sigma supremum over h 1 by n sum over I. Maybe you should have a minus 1 over n. Or let's do the following. Sigma I yi minus sigma I yi h of xi by 2. Right? Now the first term, what is the first term equal to? It's equal to 0 because sigma I is plus 1 with probability half, minus 1 with probability half, therefore has mean 0. So this is equal to 0 plus expectation over sigma. Now instead of sigma, I could just choose minus sigma. The distribution of plus sigma I is the same as the distribution of minus sigma I, because sigma is 0 mean random variable. So it's expectation over sigma of supremum over h 1 by n summation over I yi h of xi. I'll take the half outside. Sorry, this is sigma I also. All right. But so now here is the subtle part. The distribution of sigma I is the same as the distribution of sigma I yi. Right? So I claim that this is equal to half expectation over sigma supremum over h 1 by n summation over I sigma I h of xi.
Is there any reason you left the m inside?
Which one?
The one by
Inside a supremum.
What do you mean? I could take it outside also, that doesn't matter.
because you took the 1 by 2 outside.
I took the 1/2 outside because I'm going to call this whole thing something. That's the only reason. Okay, so this is what I call. So this is half. I'll just have a special notation for this RC bar of H. So this is the so-called binary Rademacher, empirical Rademacher complexity. Okay, it's just a definition, nothing else. So, in fact, this is exactly the Rademacher complexity, where I replace L of h of xi by I with just h of xi. Right? So, in the definition, the standard definition of the Rademacher complexity, I would have had L of h of xi yi. I'll just replace that with h of xi. And similarly, the Rademacher complexity of H is equal to half of expectation of RCS bar of H, just by taking expectation on both sides. And again, I'll give this a name or a separate symbol. I'll call this RCN bar of H. So it's specific to binary classification with the 0-1 loss. All right. Any questions? Now, we sort of proved, to just a quick recap, we proved this bound on the generalization error, right? We showed that with high probability, or in other words, essentially what we proved was that if, or put another way, we essentially proved this particular theorem, which said that the probability for any learning problem with bounded loss functions, we can prove that the quality of learning or your ability to learn is essentially determined by the Rademacher complexity. If the Rademacher complexity is something that vanishes as n tends to infinity, then the hypothesis class is pack learnable. If not, it's not. It may not be pack learnable. It may not be pack learnable. Right? We didn't quite prove uniform convergence, right? Because ultimately we proved that this quantity is, we proved a concentration inequality for this particular quantity. Now, to prove uniform convergence, you need one more step, which is you take supremum overall H of Rs of H minus R of H. Right? And then show that both of them are upper bound. Then it's you just take a union bound. The approach for Rs of H minus R of H is exactly identical. There's no difference there at all, because since this satisfies the bounded differences property, supremum overall H of Rs of H minus R of H also satisfies the bounded differences property. So therefore, both this and its negative are also bounded, and therefore you just get uniform convergence. Okay, so that in a sense proves pack learnability, but not completely, because we still have not determined what the Rademacher complexity can look like or how it can behave as a function of n. So the next few steps will be to show that if the VC dimension is finite, then the Rademacher complexity can be suitably upper bounded by something that decays as n tends to infinity. Okay, maybe this is a good point to stop. Let's continue in the next class.